Hi, thanks for joining me today. I've got a fun problem which combines graph theory with geometry. Suppose we colour each point in R squared either red, green, or blue. We want to prove that there exist 2 points of the same colour with distance 1 between them. So we have our xy plane, our real plane, and for every single point of the infinitely many, we give them a colour, either red, green, or blue, and we want to prove that there are 2 points, say A and B, which have distance 1 apart, and they have the same colour. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the way that we're going to show that these 2 points exist is by contradiction. So we're going to suppose for contradiction that there are no 2 points which have distance 1 apart that share the same colour. Or in other words, whenever you give me 2 points which have distance 1 apart, they're going to have different colours. Then what we're going to do is try to arrive at a contradiction. Now, when we do that, or when we think about this problem, hopefully one of the first things that comes to mind is equilateral triangles. Because if we have an equilateral triangle, say this guy here, and each of the side lengths are 1, then we know that each of the vertices of this triangle must be a different colour. So let's say that this guy here has colour red. Well, then we know that this guy here can't have colour red because it's distance 1 from a point which is colour already red. So it has to be blue or green. It doesn't really matter which. Let's say blue. Okay, and then we look at this point here. Well, now it can't be red because it's distance 1 away from a red point. And similarly, it can't be blue because it's distance 1 away from a blue point. Hence, the only colour it can possibly be is green. So if we have an equilateral triangle where each of the side lengths are 1, we know that each of the vertices of that triangle must be a different colour. And we're going to use this as a kind of tool to construct a contradiction. So what we're going to do is just take any point in our plane, let's say this guy here, and it's going to have a colour of red, blue, or green. Let's just say it's red. So this point here is red. And we're going to use equilateral triangles to kind of construct another red point. So what we're going to do is, let's say we're working in this direction. So from this point, we're going in that angle. What we're going to do is draw on an equilateral triangle, which is kind of symmetric about this line. So if I draw on this line, and so it's going to look something like this. Okay, and each of these side lengths here are 1. And by the argument we just had, we know that these two guys, these vertices, one of them must be blue and one of them must be green. It doesn't really matter which, so let's just say that this one here is blue and this one here is green. Okay? And then what we want to do is actually construct another equilateral triangle. So it's going to be this guy here. So it kind of joins back onto the line. And again, these are going to be distance 1 and 1. And again, we've got an equilateral triangle, each of the sides have length 1. We've already got a blue vertex and a green vertex. So that means that this final vertex must be red. Okay, so we've constructed another red point. So we started off with a red point. We kind of chose a direction from that red point, which kind of gave us this line here. And then we found another red point here. Now, you can use some very basic geometry just from Pythagoras' theorem to work out that this length from here to here is just the square root of 3. Okay, so from that red to that red, and the way you do that is you know that this length here is 1, so that means half of it is a half. So that means that this right angle triangle has side length half there, 1 there. So Pythagoras' theorem will give you that length there is root 3 over 2, and by symmetry that length there is also root 3 over 2, and hence the whole length there must be root 3. Okay, but what this actually tells us is that if we take our starting point, which was here, and we chose the direction kind of arbitrarily, and we look at the point which is root 3 away in that direction, that's always going to be red. So in other words, any point which is root 3 away from this red point must be coloured red. But any point that's root 3 from this guy here that just forms a circle. So if I get rid of this and draw my original point again, so this is red, then any point which is root 3 away from red, let's put it here, any point which is root 3 away from red must be coloured in red by this kind of argument here. So if I chose an arbitrary point here, then so this circle has radius root 3, then I just choose my direction to be that guy there. So that arrow there would be now this guy. And again, I could use these triangles to construct this point here, and thus this guy must be coloured in red, as do all the other points on this circle here. But this is the major problem, because I can just choose any 2 points, kind of draw on a chord which has length 1. So let's say that there has length 1, and those 2 points are both going to be red, and they are both distance 1 apart. Hence, we have arrived at a contradiction, because we suppose for contradiction we can't find these 2 points. What we've kind of shown is, if we suppose we can't, then in fact we can. So we must be able to either way. So we must always be able to find 2 points which have distance 1 apart and share the same color. I hope that has all made sense, and I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.